So remember a recap, we learned about sequences. Say that A of n is a sequence. But if I was to come and put the summation on A of n, that now becomes a series, right? And that's the first one. We have a finite series which ends at n, and we have infinite series which ends at infinity. So now I would like us to talk more about this one, number 2. So this is what we're going to be discussing most here. So we're going to be discussing most number 2. So if I was to say, let's look at some examples of the infinite series. This would be, I would say this would imply that we're having A1. If I plug 1 on R, not R, really, let me just say this. This doesn't make sense. Let's make this R, because it should be a value that allows us to plug there. Yeah. Can make this R because I'm supposed to plug here. So if I'm to plug that, I'll have A1. I plug 2, I have A2. I plug 3, I have A3. So here I would plug up until infinity. So we don't know how many times we're gonna plug. So I'm gonna put those dots up there, right? Then I come to infinite series. This would imply that A1 plus A2 up until I know where I'm gonna end. I'm gonna end at AN. You see, that's why it's called a finite series, because I know where I'm gonna end. And this one, I don't know where I'm gonna end. So that will be the case. Now, if we come here, let's say I come and say, I want to know what is how is this denoted? How do we denote this infinite series or the finite series? So let's start with the denoting. We have S of n. Now we're denoting the finite series, right? We have S of n R from 1 of A of n, R, because we're saying R there. And this would be A of 1 plus A of 2 plus A of 3 plus A of n. So we call this Sn. And then now we come and talk about S of infinity. This would be from 1 to infinity, right? So this would be from 1 to infinity. From 1 to infinity. And this would be A1, A2, A3, and so on. So now that would be how we put the summations, right? The sum of this series. So also we have what we call the partial sum. Then when we have the partial sum is when now we take, let's say I take the sequence of these sums, call them S1, S2, S3, and doesn't matter how many I take. And then we'll call these partial sums. So we'll discuss more of these when we come to things like telescoping and geometric series. We'll talk more about the partial sum when we get there. Now, we can say that this partial sum So this I can call it this machine. I can call it this, right? I can say that the sequence of this series, right? So I can call it sequence of series. Can call it sequence. The reason why I'm calling it sequence of series, you know that this stands for what? For the series, the S, right? And then this Sn will stand for the sums. And then this brackets will stand for a sequence. So I'm saying that this is a sequence of series. Right? Then I'll say the sequence of series, let's say if the sequence of series converges, then we'll know there will exist a certain number. Even that we know with sequences, if this sequence, if the limit of the sequences, so if the limit of these partial sums, right, exist, it means that they converge to a certain number. If they converge to S, it means that they exist a certain number, right? If this converge to a certain number, then the number should be S. With the sequences, we used to say that if the limit as n approaches infinity of a of n converges, then it should be equals to a certain number n. You remember, right? So we used to give it such a concept. Now when it comes to series, we can say if the limit of the partial sums converges, then there will exist a certain number S, right? Such that S is an element of a real number. And then if, so let me write that statement here. I'm going to say if let's say converges, and then they exist as element of a real number, such that alright, then we know that if this now does let's say if this now does not exist, right? If this does not exist, you remember, if a limit does not exist, then we can say it diverges, right? Then we can say it diverges, and then the series diverges. If it does not exist, then it diverges. So we learned that from the previous topic. Now let's come to the first part. Remember I said that the first one which we have is geometric series, right? Now we can jump to geometric series. Now we can jump to geometric series. So when we come to geometric series, we're gonna be talking about Sn. So we have a formula. We can have Sn to the n. So we're gonna always try to formulate this formula, or try to make sure that we compute our sums using this formula, right? Then we have r to the k minus 1. So it's k minus 1 if it starts from 1, and it's k. Let's do this. I want us to do this. Let's assume that now I take this k. Let's do this. This is the same thing as if I take this k, this 1 to the left, I'll have k equals to 0. Is that right? And this would be a to the r. K minus 1 is equals to what now? 0. You see, right? So now means that, but let's focus on this one. So if I would take that to the other side, I would get that. Then, but let's focus on the first one. And then this would happen only if, now let's say we can, let's say, okay, let me maybe I can try to show you how. I know some of you know this formula, right? This one off. I can try to show you how we can get that formula. We know this formula, some of us. I'll write it here. We know this formula that Sn is equals to A. That 2, right? You know this. You know this formula. I'm sure we agree there, right? Most we know that formula, right? And then also some know this one, right? So it is, so we could show how this formula came about. And also this one, it's gonna be simple because we have to use now intervals to check which one is which one, right? We can use intervals to check. So now the formula that we're gonna be using are 2. So we're gonna be using this and the first one. And this one forces us to bound r, saying that r is not equal to 1. Because if r becomes 1, the denominator will be equal to 0. So we are forced to bound this one. So check, the first one has this. The first one has the summation. Then the second one doesn't have the summation. So the second one will depend, right? Let's say now I take the limit. I take the limit as n approaches infinity. You see, right? If n approaches infinity, I'm gonna have this. The limit I'm taking based on this one. Because this is how the question is gonna be given to us. Then we should change it to this. Then we apply the limit. You see, right? Then we'll say n is equals to infinity. Then we're going to say I have a outside r to the n minus 1 over r minus 1, right? Then here I'll say, we know this, I'll say that now we know that r is not equal to 1, all right? If r is not equal to 1, it's either r is less than 1 or it's greater than 1. You agree, right? So I'll have to have 2 solutions for this. So it's either r is less than 1 or it's greater than 1. So if I come and have r being less than 1, if I come and have r being less than 1, the question is what will happen? Let's say r is less than 1. What do you think will happen? Anyone? If r is less than 1,
we're going to get a negative answer.
We're going to get a negative answer, right? So it means that this would be like this. This would be negative a over r minus 1. And factoring out the negative would get a over 1 minus r. You agree, right, ne? So we agree with this one, right, ne? If r is less than 1, this one will be bigger. And then this will take us to a negative answer. So, because this one will always be 0 comma something. Even if this is even, this would be 0 comma something. And then, now we check. So here we say that when r is less than 1, just that here they're using the summation, the absolute value of r. So they are assuming that r might stay positive. So now, if r is greater than 1, then what do you think would be the thing? You see, this one now would become, if r is greater than 1, if we have 2 to the infinity, that would remain infinite. You agree, right, ne? So that will be the case. So we're going to say this will remain infinite, it will diverge, given that the summation of the absolute value of R is greater than 1. So I just wrote this part so that you can see that this was negative. How did this R minus 1 change to 1 minus R? It's because we factored out negative. So now you see this tells us that the geometric series, so let me say so I can write the summary here. We can say that summary for geometric series let's say we computed this limit of the summation, right? And then after computing this limit of the summation, we find that we're getting that the absolute value of R is less than 1. So we say that if the absolute value of R is less than 1, we can say the series converges. You say, right? Then if the absolute value of R is greater than 1, the series diverges. And it will also diverge when this is equal to 1. Reason being, we know R is not supposed to be equal to 1. You see? So that will be the case. Now this we know. So let's take an example. Alright? Let's take an example. So I'm going to use the examples that they used in your guide. Then I explain. Yeah. So we're going to have the first example. Now we're given this summation, they say, we're given the summation of 8 n from 0. Then we have 2 times 1 over 5 to the n. If we check, this is in a bit of this part. You see, right? So we know that if I expand this, if I try to expand this, I'll get, if I plug 0 there, I'll get 2 plus, now let me show you something. This would be summation n equals to 1. Now n will start at 1, 2, 1 over 5 to the n. You see? And this will be the same. If I continue to plug, if I plug a 1 now there, I'll have 2 over 5. If I plug 2, I can have 2 over 25, if I'm not mistaken. And this, plus if I plug 3, I'll have 2 over 5 to the 3. You see, right? And then, now let me take a calculator. I need to check this. So if I do this now, I come and try to divide this, right? Let me try to divide this. I take 2 over 5, divide by 2, I get 1 over 5. We agree, right? Then I take 2 over 5 squared, divide by 2 over 5. I'll still get 1 over 5. And then I still do the same thing here. To the third over squared, I get 1 over 5. So since these values now are the same, it means that this will be our R. You agree, right? And this does not just become our R, it also allows us, as long as they're the same, it also allows us to take this as A. But let's assume that this was a different number, right? then these ones were the same. It would allow us to take this as A, then put this one aside. Then we're going to edit later. So you can find some that are different. I'm sure we can come across such along the way. So this allows us to say that now I can say that A will be 2 and then R will be 1 over 5. Then that means that we can take the summation, the limit as n approaches infinity of Sn of equals to the limit as n approaches infinity of this summation where the R to the n, right? 1 over 5 to the n minus 1 over, then we had 1 over 5 minus 1. So remember what I said here. I said you're gonna be taking this to this. Don't just jump to this. You see, right? You're gonna be taking it step by step. We take this to this. Then we check now what is our value of R. Is the value of R less than or greater than? You see? Less than 1 or greater than 1. So we see that the value of this is less than 1. So this would force this to be 0 if it's less than 1. Right, we have the limit as n approaches infinity of 2, 0 minus 1 all over 1 over 5 minus 1 is what? Four over 5, right? Minus 4 over 5. So this would be equals to the limit as n approaches infinity of minus 2 over minus 4 over 5. You see, when that R is less than 1, this always becomes negative. You see, right? So that's why I wrote that part of negative there. And this would become, the answer here would be minus 2 over minus 4 over 5. And this would give us 5 over, is it 5 over 2? Yeah. So now we got 5 over 2, right? Then we're gonna check the summation of 5 over 2. We're gonna check 5 over 2, right? That means that this is the limit that this thing converges to. Remember this definition that says automatically we knew that R is less than 1, right? Therefore the series will converge. But then we want to know the partial sum that it will converge to. So remember this says that if the sequence of series Sn converges, then they will exist as element of R, such that this will be the case. So we're interested into finding that S. You see, right? Even though we knew that it would converge, then we know that it converges to 5 over 2. You can say therefore the sequence of series converges to 5 over 2. You see, right? Then we consider the second example. Now they give us this now. They say S of infinity is equals to 4 minus 1 plus 1 over 2. Then they say minus 1 over 4. Then they say plus 1 over 8 minus 1 over 60. Right, and then plus. Then remember here what I did, right? Remember I wrote this. I said that the definite series the definite series we put it like that, we did not like that, and the infinite series we did not like that. So the first example was based on finite series. Now we are going to be based on infinite series, right? And then now we do this. Want to check I want to check this. So we say, I'm going to do this. We say minus 1 divided by 4 would be minus 1 over 4. You agree, right? And then 1 over 2 divided by minus 1 will be minus 1 over 2. And minus 1 over 4 divided by 1 over 2 will be minus 1 over 2. And minus 1 over 2. Minus 1 over 2. If this is the case, remember, this is not the same as this. So this series only allows us to take A as this one. You see, right? It only allows us to take A as that one. So it means that we have to cut off this sequence. So we're going to say this will be, we're going to consider minus 1 plus 1 over 2 plus 1 over 4 plus 1 over 8 minus 1 over 16. You see, right? Then we're considering this part. And we know from that part R, not really R, let's take the absolute value of R. We need the absolute value of R. The absolute value of R will be less than 1 because it's 1, it will become 1 over 2, right? So I can say this equals 1 over 2, which is less than 1. So this thing already, it converges. We know that it converges, right? Hence, so when they ask you, is this, does the series converge or diverge? By geometric series, you don't have to go through all the computation, right? Hence, the series converges. Right, so remember what I said there? It converges. But the question is, what does it converge to? That is the question. You see, right? What does it converge to? So, we're going to say, now we'll take this and say, let's say we name it, we say, so, we'll say, minus 1 plus 1 over 2, 1 over 4 plus 1 over 8, plus 1 over 16, plus. This will be equals to, right? And then means that we can say this will be equals to, we can have the formula, say minus 1 over, then we'll say 1 minus, our R is what? Minus 1 over 2. And this will be minus 1 over 1 plus 1 over 2. That will be 3 over 2. And then this will be minus 2 over 3. You can try to simplify that with a calculator. Right. So this will give us, will force us to have this the S of that, which will be equals to, now we take that 4 from the beginning. You see, right? We say 4 minus 2 over 3. And this will give us 10 over 5. So you see that this one converges. Can say thus the series converges to 10 over 5. You see, right? Then we know the series converges to 10 over 5. And then now we come to we have this now. Hey? Is anyone who's speaking?
The answer must be 10 over 3.
Should be what?
10 over 3.
It's 10 over 4 minus 2 over 3. It's 10 over 3. Oh yeah, it's 10 over 3. So now I given this, they say we should find the summation. I think it's k from 1, and then we have 4 to the k times 3 to the 1 minus k. Yeah, so we need to find this now. So the best way, right, is to start by expanding this. We know that. So if I plug 1 there, I'll get 4 plus, if I plug 2, I'll get I'll get 16 over 3. If I plug 3 on k, I'll get 64 over 9. If I plug 4, I'll get 256 over 27. If I plug 5, I'll get 1024 over 81. It ends at infinity, so I'm gonna put those dots. You see, right? And then now I can try to check for my r. I want to see, can we take the first value as a or not? You see, right? That means that if I take 16 over 3 divided by 4, I'm going to get 4 over 3. Then I do the same thing. I take 64 over 9 divided by 16 over 3. I get 4 over 3. You see, right? 4 over 3. 4 over 3. So this allows me to now come and say this is our A, because these are the same. You see, right? It's a bit different from the previous one. So it means that I'm going to say summation of r is equals to 4 over 3, which is greater than 1. And this, thus, the series diverges. And we know that if the series diverges, then there's no s that we need to find. You see? So there's no need for us to go and find s if the series diverges. So we have like 15 minutes left before we end the session. So now we come to telescoping series. The reason why this one becomes my favorite part is because it causes us to apply the concept of mathematics, and it needs you to think. Yeah, so this will cause us to go back to partial fractions, and you'll find this if you're going to be doing maths in your final. You'll find this, that the sequences. That's my test 1. I'm gonna be writing with this on test 1. Let's hope I top the charts. So now we're given this first question. They say we're moving from 1 up until infinity of 1 over n plus 1 minus 1 over n plus 2. Yeah, so now we need to, what this tells us is that we need to for us to compute this, we need to find the partial sums, and the partial sums are Sn is equals to. So that's how the partial sum is gonna be. So now the question is, how many values are we going to, or how many times are we going to expand this? So first thing that I'm gonna tell you is that you must expand this 3 times. You see, right? And then the last part will be based on this. So now if I plug 1 there, I'll get 1 over 2 minus 1 over 3. This is 1. Then I expand it for the second time, 1 over 3 minus 1 over 4. If I plug 2, then this is the third time. Then I get 1 over 4 minus 1 over 5 plus, then I expand it. Then the last part will be based on this. So now I'll be forced to plug the opposite of this, n minus 2. You see, right? I'll be forced to plug n minus 2. So I'll have, if I plug n minus 2 on this, on n plus 1, what am I going to get? N minus 2 and n plus 1, going to get n minus 1. We agree, right now? Then if I plug n minus 2 here, I'm going to get minus 1 over n. Plus, then I'm going to get, if now from n minus 1, first here I plugged n minus 2, right? Then nextly I'll plug n minus 1. So this is going to be increasing by 1, you see, because you remember this was increasing by 1. Then now I'm going to be plugging n minus 1. If I plug n minus 1 here, I'll get 1 over n. Minus I plug n minus 1 here, I'll get 1 over n plus 1. Now I'm gonna be plugging until I get to this point. Then if now I plug, it was n minus 1. If now I plug n, I'll get n plus 1 minus n plus 2. So check this. I expanded 3 times below. So this happens sometimes. If this happens, just know you got a perfect one, right? Then this I plugged n. So if I check, I need to cancel the ones which are the same now, you see. So if we cancel twice, let me show you something. If you cancel this, and we cancel this and this, trust me, we have to leave the other ones because they're gonna cancel. As long as these ones are canceling. So that's why I say you should expand 3 times. So we're gonna be fine as long as we cancel this 4 in the middle, you see. And also as long as we cancel this 4 here, we'll be fine. So this will be fine. So as long as this cancel, this one just know it's gonna cancel also with something else. Just know that also this one is gonna cancel. So we're gonna take this and this. So we'll say that the partial sum will be 1 over 2 minus 1 over n plus 2. You see, right? That will be the partial sum s of n. Then now we need to find the limit of the partial sum. Right? We say the limit as n approaches infinity of Sn will be equal to the limit as n approaches infinity of 1 over 2 minus 1 over n plus 2. We agree, right? And then this will be 1 over 2 minus 0, which is 1 over 2. You see, right? Then we know that, you see, so the series converges to 1 over 2. You see, right? Simple as that. So now let's come to the second one. We have like 9 minutes left. Exactly at 4 we should stop. Then I think this will be the last one. Then we have the summation from n equals to 1 to infinity of 3 over n plus 2. So the only way we can apply a partial sum, a telescoping series, is when we have something like a over this minus b over this. That's the only way we can apply telescoping series. So if we find a series like this, we need to say like this. We can say, means that I can come and say, let me say, by a partial fraction, three over n plus 2 is equals to a over n plus b over n plus 2. This means that I need to apply partial fraction. Then I divide by this both sides. Here I'll be left with 3 is equals to a n plus 2 plus bn. You see, right? Then this will be the case. Then here we have the case where if n is equal to minus 2. If I take this equation to 0, I'll get n is equal to minus 2. You see, right? Then I'll have 3. This will be 0. And then I'll have 2 to minus 2b. Then this would imply that b is equal to minus 3 over 2. You see, right? Then if we have n be equals to 0, if I take this equation to 0, I'll get that n is equal to 0. Then I'll get a will be equals to 3 over 2. You see, right? And then this would be, now we know that this would imply that 3 over n plus 1 would be equals to 3 over 2 over n minus 3 over 2 over n plus 1. And this would be the same thing as 3 over 2 to 1 over n minus 1 over n plus 1. You see, right? Then this would be the same thing. Then it means that when we come back to this summation now, we know this would imply that the summation...
How do you put that n plus 1 equals to n plus 2?
What? Oh, it's plus 2, ne?
Yes.
Oh. Is it fine now? Yeah, so it means that we have 3 over n plus 1. This would be equals to, that means that now we would have this, the summation. Don't forget we only substitute this, right? The summation from n equals to 1 of 3 over 2, 1 over n minus 1 over n plus 2. So this will be 3 over 2 we need brackets if we're putting this because there is a minus in between, right? Even if you write a plus, we need brackets to cover both terms. So since we have this, now we can apply the partial sum. You see, right? We have 3 over 2. The partial sum will apply it inside this bracket. So I said that we have to expand twice, right? So we have 1 over 1 is 1 minus 1 over 1 plus 2 will be 1 over 3 plus 1 over 2 minus 1 over 4 plus 1 over, is it 1 over 3 minus 1 over 5, right? Is it like this? Let me check. Yeah, it is, right? If I plug 1 there, if I plug 2 I get 4, if I plug 3 I get 5. Yeah, it's correct. So this will be the case, right? The unit in between the distance there, it's 1 over 2. So now I have this, right? The first 3 terms. Remember I said that we expand the first 3 terms. Then I want to expand the last terms. So I'm going to focus on n minus 2. I'll start by plugging n minus 2. So I get 1 over n minus 2. Minus, if I plug n minus 2 there, I'll get 1 over n. Plus, I plug another n minus 2. I get you. Now it's n minus 1 because it's decreasing. It's increasing by 1. So now it's n minus 1 minus, if it's n minus 1, that will eliminate and get 1 n plus 1. Then now I plug n. You see? Then this, let's check which ones cancel. this cancels, right? And then so here's the concept, right? We're interested in this. If this does not cancel, just know that this one will. You see, so I don't have to expand it a lot. So here I'm only interested to check whether will the second one also cancel, the first one in that list. So we usually don't care about these ones, the second ones here. You see, what we're interested in is this one going to cancel. You see, the first one here in the list didn't cancel, the second one didn't cancel, but the third one canceled. It means that from the third going up, they will cancel the first ones. You see, so also these ones, they cancelled from the beginning, means that they will cancel going forward. You see, right? So what I was interested in is to check if this one will cancel, but that 1/2 didn't cancel, so the rest will cancel. And 1/3 cancelled from here. You see, right? So I'll just cancel this with a different pen just to show you that these ones, since they cancelled from here, they'll cancel going forward. And since this one cancelled from here, going forward they'll cancel. So now we come to these ones here. We have this cancelled with this. Which one again? Yeah, so these ones, let's check. Now I'm gonna try to check the sequence, right? So check this. I'm gonna check like this. So this, I'll match it with the last one. You see? Then this, I'll match it with this. This 1/2, I'll match it with this. This 1/4, I'll match it with this. This 1/3, I'll match it with this. This 1/5, I'll match it with this. So let's check this. So let me do this. I think it will be better if I use this. I'm matching one with this. Also, I match 1/3 with this. Then I match 1/2 with this, right? And then I match 1/n with this. Then I match I match this with this, and again I match this with this. So the ones that did not cancel from here, they also won't cancel here. You see, right? So let's check which ones didn't cancel. So this thing of matching, we could also do it from before, right? And it could work. Just that those ones were so simple that we didn't have to match. So we have 3/2. One didn't cancel, I'll keep it. 1/2 didn't cancel, I'll keep it. The rest cancelled, you see. Then I come back here, I check what is 1 matched to, or let's start with 1/2. 1/2 is matched to minus 1/n plus 1. You see? And also, what else? Oh, 1 is matched to minus 1/n plus 1. You see, right? Your n plus 2, not 1. You see, right? So that's the case. Do you guys understand? Yeah, so this is the last one. We're supposed to stop now. So I'll have the limit as n approaches infinity of Sn 3/2. The limit as n approaches infinity of 3/2 minus 1/n plus 1 minus 1/n plus 2. And this would give us what? Would give us 9/4. We agree right there. So we know that this sum converges to 9/4. So we can stop here. Next time when we come, we'll do harmonic series. Any question? So I'll send these notes now and also upload the recording and send it.